This is question 2 for the OCR Depth in Physics practice paper. Question 2 is about an experiment to determine the acceleration of freefall using a steel ball, electromagnet, trapdoor here. The electromagnet and the trapdoor are connected to a circuit that will operate a timer. When you switch the electromagnet off, which will release the ball, that will start a timer. And when the ball hits the trapdoor, that will break this contact and stop the timer. So we've got an automated way of starting and stopping the timer to eliminate human reaction time. Now let's go down here to see the time values that we've got, times and distances. The experiment is repeated for different heights above the trapdoor for the ball to fall through, so that you get a range of height and time data. And then the mean times are given to us in this table, and they're squared, so we've got s and t squared, which is then used to plot a graph. The first question, A part 1, requires us to complete the table, so you can see that we're just squaring the time values to fill this table in. So those values are 0.22 and 0.26. We're going to write those in. 0.22, 0.26. Complete the table. That's the first part. Then we need to add 2 final points to the graph. Here's the graph. So this is our graph S against t squared there. We can just about make out a point there. There is a point there. I will just go over that a little bit, see if I can make it a little clearer. There we go. And yeah, so we've got S against t squared. 1, 2, 3, 4 points there. You can see that my 2 points are going to go in there. And once I've plotted those points, I need to do draw a line of best fit. So we've got the first data point is at 1 and 0.22. So the values are systematic along this axis. So 1 and 0.22, so 0.2 is there. This is 2 small squares to 0.01, so that's going to be 0.21 there, 0.22 there. So that would be here. So we're going to plot that. And next one is 0.26, and that was at 1.2, so that would be there. Now I need to draw a line of best fit. That was the third thing that was required, and that's why it's 3 marks there. So I've done the graph plots and then the line of best fit. It's going to be a little bit tricky to do on a tablet. I'm going to continue the line down to the x-axis, and you can appreciate from this probably that these plots are lining up very nicely, but not through the origin, so your line must not go through the origin. It's a little bit tricky on the tablet, but yeah, that's pretty good. So my line is crossing at 0.02. That looks pretty accurate. Yeah, so that's a line of best fit there, straight line of best fit. Now we're asked to determine the gradient of the line. I'll just go back. I did do that, so I'll tick that off just to be consistent, and I'll rub out my little practice mark there. Determine the gradient of the line. Show clearly you're working. The working that I need to show here is the triangle that I use to work out the gradient. I've already indicated that this is going through 0.02 there, and I can use this plot up here. Key thing is to have a nice big triangle drawn on the grid so that the examiner knows that you used a triangle to work out the gradient, and that it was big enough to get an accurate measurement. You don't want a little triangle down here. You want to choose 2 points that cover more than half of the line that end on easy to read points. So I'm going to draw a triangle here. Okay, so the gradient calculation. Gradient is y2 minus y1 over x2 minus x1. The y values are 1.4 and 0. So 1.4 minus 0. And x2 is 0.3 and x1 is 0.02. 0.30 minus 0.02. So that would be 1.4 divided by 0.28. That's 5. That's my gradient calculation. Right, next part. The student expected the line to go through the origin and have a gradient of g divided by 2, which g is 9.8, so that would be 4.9. The timing device he used measures to within 0.01 seconds, and the distance s was measured to within 0.01 meters. The fact that the line of best fit does not pass through the origin is unlikely to have been caused by random errors in the measurements. Justify this statement. First thing we're going to do here is that if you can see these points, they're all lining up nicely, and yet the line doesn't go through the origin. All the points are below where they should be if they were to go through the origin. So because the same error is in all of the points in the same direction, that indicates that that's a systematic error. So that's the first thing we're going to say here. All plots are below where they should be, therefore there is a systematic error. That's different to random errors. You have systematic errors and random errors, so if they're not likely to be random errors, then we're looking for evidence that they are systematic errors. So that's the first bit of evidence. Now if we look at the plots, because they're all below where we expected them to be, what we're going to do is we're going to use the uncertainty of the S measurement, which was 0.01, to draw some error bars and see if they could account for the uncertainty, the fact that it doesn't go through the origin. The error bars will give us the range over which the plots could have reasonably fallen. Now the uncertainty in S was 0.01 meters. Now if we look at where that would actually be on the scale, so 10, this is 0.04, 0.4, 0.5, so that means one small square here is 0.02. 0.01 is our uncertainty up there, so that's half a small square. So what uncertainty is there in the plots? Well, you can see it's going to be very, very small. If I can indicate that on here, something like that, like that. Okay, you can see that there's not much uncertainty there. Very little scope for actually the line shifting very much at all due to any uncertainty in S. And the line of worst fit that you could use, where if you took the very extreme point of plotting these as low down as they could be and lower here, and then plotting them as high as they could be here to rotate the line around, that wouldn't give you a line still that passes through the origin. So the error bars do not allow for a line that passes through the origin. That's what we need to write here. error bars don't allow for a line that passes through the origin. I should have said a line of worst fit that passes through the origin. Those are the 2 points that we want to make there. So we've shown evidence that the error is in fact not random but systematic, and then we've also said that even if we factor in random errors from the uncertainty, that wouldn't give us a line that passes through the origin. So now on to statement 2. Explain how systematic error in each of the measured quantities could contribute to the line not passing through the origin, and what effect, if any, each would have on the gradient of the line. If there was a systematic error in S, which from here we can see all the F, and we've already stated, it looks like the S values are smaller than they should be. And further to that point, the S values are plotted directly on the line. So we took the measurements for S and then we plotted them. So there's no calculation done in between. That means that if there is an error, each plot is affected by the same amount. So we are answering the question, explain how a systematic error in S could contribute to the line not passing through the origin. The S values are too small. But because they're all affected by the same amount, or all changed by the same amount, that would not change the gradient. S values are all changed by the same amount, so there is no change to the gradient. That's the first 2 points that we want for our 2 marks there. How the systematic error would contribute, and then no change to the gradient. The t values, so these t values, and this is a little bit trickier, because we measured t but t squared is plotted. If there's a systematic error in t, then when you square that, the amount of change will be different, so that would change your plots. If the t value is bigger than it should be, then the change will be compounded. So that would, t squared would make the change bigger, and that would have the effect of spreading your points out in the x direction more than they should be, and that would reduce the gradient, that would decrease the gradient. Although that is actually different to what the mark scheme says. In the mark scheme it says t is too big, constant error in t leads to increasing error in t squared, so gradient is changed, or it's steeper, so the gradient is steeper. I think that if t was too big, leading to an increasing error in t squared, that would make the gradient less steep, but maybe I've misunderstood that. Now, let me stick to the mark scheme here, and this is what the mark scheme says. T is too big, a constant, that's the first point. The second point is constant error in t leads to increasing error in t squared, so the gradient is steeper. Now, what they mean by increasing error in t squared is not clear, but I think what they're saying is that these points are closer together than they would otherwise have been. So if S is unchanged, then that would make your line steeper. They do say that the line is steeper than it should be, so I think that that's what they meant by that. So let's go with that. T values are too big. A constant error in t leads to an increasing error in t squared, so the gradient is steeper. After some further deliberation about B part 2, I've decided that I think the mark scheme is incorrect here. We're looking at the error in t and its effect on t squared. I agree that there are valid reasons for t being too big, which we've looked at from the experiment, but the effect on t squared is not as the mark scheme would say. So if t values are too big by a systematic error, we get a constant error in t, but when you square those, that will make t squared larger than they should be by increasing amounts as you get to larger values of t squared. So that's all well and good, but if you look at the graph, if these values for t squared, which are plotted on the x-axis, are getting increasingly too big, that would spread your points out in the x direction, and that would then mean your gradient would be smaller than it should be. So not steeper as the mark scheme says. So that's the reason why I think that it's incorrect. And I will show some example values to prove that is what would happen. It would be spread out in the x direction. So on that point, I would say the mark scheme is incorrect. I have seen a few other places that the mark scheme is incorrect, and I think that adds further weight to my reasoning here. Suggest one source of possible systematic error in the experiment. For the last part of the question, if we look at the equipment we were using, we're releasing the ball with an electromagnet. Well, whenever you switch an electromagnet off, it takes a short time for the field to collapse and therefore release the ball. So that's one thing we could say. That would increase the time because there'd be a delay between switching off the timer and the ball being released, so that would make t too big. When the ball hits the trapdoor, there's going to be a slight delay between it hitting that and breaking this contact here, which would also increase the t. So that's what we could say either of those 2 points. Time delay between switching off the magnet and the ball starting to fall. That makes t too big. There we go, that's question 2, and later I'll do another video for question 3.